I took out of the internet this nice picture of KTH in Stockholm. And this is a message like, a postcard. I would like to be there today. So thank you very much. Thank you also to Professor Hans-Peter Nee to contact me about this. But before going any forward, I would also like to credit my colleagues from University of Catania, Italy, Professor Santirizzo and Dr. Giovanni Susini, who has been contributing to this investigation about modern condition monitoring methods. First of all, I would like to give you some introduction about the Aalborg University. I hope you will be interested in this. It is an average, I would say, size university. We have 5 faculties, among these energy and science, which I belong to. And as I mentioned before, it's average size university with 23,000 students, basically 10% of them part-time, and quite a large number of PhD students, around 850 all every time, of course, varying and changing. You can see a nice number of staff members, and there is a good reason for this, because in Aalborg University we adopted what is called the problem-based learning approach, which means that teaching is made by groups, by student groups, and there is a frequent interaction also outside the teaching hours. So this calls for a large number of teachers, and this is why we have a ratio which is around, I would say, 1 to 10, 1 teacher per 10 students. Quite remarkably, we have a large percentage, I would say 30% of foreign staff members, which is, I would say, quite a good result. 1,200 and more administrative staff, and a budget of around 2. Let's say 3 million, sorry, billions DKK, Danish crowns. Aalborg University is spread over 3 campuses. The main one is sitting in Aalborg City in the north region of Jutland Peninsula, and with almost 20,000 students here. The second one is in Copenhagen, about 3,000 students here, which is focusing mostly on teaching. And the third one is the smallest one, though I would say rather strategic, because it's situated is located in Esbjerg city, which is very important in Denmark for production related to wind turbine market. Quite proudly, I would like to show this slide with the very nice results we achieved according to the US ranking 2020. We scored the second best university in the world, the first in Europe, about the schools of engineering. And also according to the more recent THE World University ranking, we scored the #1 in the sustainable development goal #4, which is quality of education, and #6 overall, which is also making us quite proud, I would say. A few words also about CORP, the Center of Reliable Power Electronics. You can see the logo here. These are some achievements. So basically it is a center inside our department here at Aalborg University, working on reliability, specifically on reliability of power electronics. And as MIETEC has kindly announced, we try spreading a little bit the knowledge and the, I would say, scientific importance of reliability of power electronics. You can see some figures here, and you can see that also one of the goals is to keep organizing events and disseminations. Spreading the culture means also writing books, editing special issues, and this is one case I would like to draw to your attention. Is a recent achievement of CORP, the Center of Reliable Power Electronics, is an edited book about modern power devices, including, for example, vertical gallium nitride components, which are not that popular yet. Another interesting achievement of CORP is the initiation of a newly founded journal specifically on power electronic devices and components, where it is an open access, by the way, journal, and you can get 100% publication fee waived by 31st, of March 2022, which is probably a very good place also to disseminate what's going on in condition monitoring, very likely. Last but not least, let me invite you all to the Corp thematic days, which are going to be held tomorrow, actually, and the day after tomorrow, from 1 p.m. 4:30 p.m. European Central Time. Participation is free of charge. It's going to be virtual, and we have two keynote speakers from industry and academia. One of them from Vestas, and the other presentations will be from people belonging to Corp. So you all are welcome to join. Okay, so thank you for bearing with me with this introduction about Aalborg University. Oh, by the way, I put some catchy pictures, in this case a movie. I hope you can see the movement here. Mietek, please be kind to confirm you can see the motion here.
Not yet.
I was in doubt because
yes, small movements.
Yes, small movement. Yes, this is a nice movie we took with the fast shooting camera during power cycling, and you can see we have two bond wires here, actually three. This is number one, this is number two, this is number three on the background here. And for the sake of reference, we put a needle. You can see the needle tip here, which is fixed on the let's say on the holder, on the base plate, and you can see an optical fiber here, which is mechanically connected to the bond wires, and you can see what happens during power cycling. So this is a little bit, I would say, the reason of wear out of components, and this is the reason why we need condition monitoring, basically. So my talk will be introducing first a little bit what the importance of condition monitoring is, and then basically listing up the most popular and well-established methods for condition monitoring and coming applications. And then I'll be digging a little bit more into details of acoustic methods, optical methods, physical methods, electrical methods, the more the better, and finally drawing some conclusions. Introduction first. So power electronics is obviously, I would say, an enabling technology. It has become recently an enabling technology. The reason is very simple. We are moving to renewables, which means that our sources of energy like wind, like solar, photovoltaics, but also other, for example, sea energy, wave energy, and so on, they're all of them changing in time. They're not constant. So on the one side, we have a non-constant energy sources. On the other side, you have a very, very constant frequency and voltage demands, for example, in case of a national grid. So what you need to do in between is, number one, to provide storage, which is very important because you have to accumulate energy when you do not produce it, but still utilize it, and then opposite. And the other thing you need is to equalize, I mean, to make uniform as possible the energy parameters, which are not constant. So wind speed is changing, solar irradiance is changing, but you need to feed constant, as I mentioned before, frequency voltage to the grid. So you need to condition this, and the only way we know so far is to turn everything into electricity and then condition. And to do this, we need power electronics. But power electronics is also taking part in transmission, which is not the topic of today's webinar. For example, power electronics transformer. It is also part of consumer electronics, so utilization of energy. So power electronics has become really, really, really an enabling technology. As such, power electronics needs to be reliable. And this means that we have to find a way to elevate the expected number of operational years for I would say a decade or more. So you can see here some optimistic predictions, not predictions, actually, not yet, I should say, but wishes in terms of reliability and life extension, lifespan of power electronics. And you can see that power electronics is largely competing with, for example, traditionally highly reliable industries like aircrafts or heavy train applications like this. So it is quite a message, I would say, thinking of photovoltaics and wind turbines aiming at 25, 30 years lifetime, which is incredibly large because, you know, when I teach to my students about reliability, I always say, I don't really know where I'm going to be in 25, 30 years? Really, no idea, no clue. So how can I be in control of where my power electronics is going to be? It's very challenging, very difficult. Of course, it is possible to make lifetime models, lifetime prediction, but I would say this is the key reason why condition monitoring comes into play. We want to monitor we need actually to monitor our power electronics. It's not possible otherwise. So condition monitoring. I put as a title 2 decades of condition monitoring. This one is a little bit controversial. You may argue it is more than 2 decades. Yes, I agree. But I would say from year 2000 on, we started taking condition monitoring, I would say, seriously. So there has been the first applications of condition monitoring. In particular, everyone knows about on-state voltage measured at high current, on-state voltage measured at low current, and so on. And then after these, which were, I would say, the first of all, by the way, contact methods, I will be discussing about like physical methods, measuring directly, chip temperature with thermocouples and something like this. But after these, then a lot of new concepts have been flourishing over the last 2 decades. And you can see some examples here: diodes, embedded diodes, threshold voltage drift, dynamic methods like turn on and turn off delay times, DIDT, dV by dt, also diagnostic methods like infrared camera, more, I would say, future and I would say ambitious methods like acoustic detection. I will spend some words about fiber optic, photodiodes, and more and more and more and more. What's next? This is also a nice question. Well, I will try showing you how important is not just monitoring what the condition is, but also be able to work out some conclusion out of it. To do this, we need, first of all, to communicate. So we need to put everything, connected, which is not happening yet. Our power electronics are isolated for the entire life, and this is something, by definition, inhibiting condition monitoring. We need the artificial intelligence. We need something able to make decisions based on condition monitoring, and probably we need also computational power. And this is why I also wanted to mention cloud computing. So this is kind of a roadmap where we were, where we are, where we are going to be probably in the next maybe 5 years or 10 years. Just to classify a little bit what condition monitoring methods are, basically you can see there is a large majority of them working by thermal monitoring, which means basically temperature. And this is for good reason, because I don't have time to, but I think it is largely shared that the main killer of power electronics is temperature and temperature swing. So if you monitor temperature, basically you are monitoring what the root cause is. So at least you can log it, you can figure out what's going on. And if you're lucky, you can also cross-correlate with other parameters and work out the state of health. Temperature is not everything. As I mentioned again and again, there are also other emerging techniques like acoustic methods. So I will be spending some words about this. Just to roughly classify the thermal methods, I put basically 3 main categories. The first one is optical, very promising, and the reason is obvious, because you don't have galvanic isolation. You don't have galvanic contact. You have intrinsic galvanic isolation, which is very much demanded, because you don't want to affect your power electronics reliability because of your monitoring unit, right? So galvanic isolation is very key. You have a contact methods, which is basically physical methods or thermal test chips. I'll be spending some words about, and very, very much of them is indirect methods like temperature sensitive electrical parameters, which all of them have basically in common the ability of working out what the temperature is starting from electrical parameters like voltage and current. You have a list here for your future reference. So a few words about why I was thinking of, infrastructure, communication infrastructure for condition monitoring. Basically, the reason is very simple. If you think of your power electronics unit like this red one here, You have your converters in your devices you would like to monitor. You have condition monitoring sensors, and then you have a controller, which is basically not just a controller, it's rather an interface, because this unit is, of course, in charge of controlling and making sure the function is brought ahead, but also it has a communication function with the other world. So if we move one level up to the other world, then we need what is called a service provider or a provider of service, you can see here, which is able, to collect this data from the controller system interface, to transmit them to the closest central station. And then, of course, you need a process. So you have condition monitoring data. So what? You need to compare probably with a database. You need to compare with a data storage or something like this. You need to work out models. You need to make decision. So this is why you need artificial intelligence. And then that's not enough. Once you made a decision, then you have to go back to your system and, making actions, which can be stopping in the worst case, in the worst scenario, but it can be also reducing power in the case it can bear with it, or something like this. Scenario is even more complicated because you have an external communication infrastructure. So you are here, the yellow, the provider of service is here, but this one is supposed also to be interacting with other, big entities, like, for example, the enterprises, like research center to provide data, online and offline data, but also, with security agencies, because, when you put everything over the internet, you have seen this big accident in the US about the, I would say, I think it's water pipeline in the southeastern part of the country, where they had a hacking attack and they had to stop the plant because of this. So big problem also about security, and of course public institutions making decisions, strategic decisions in terms of quality of service and something like this. So we have to think of condition monitoring as a brick of a very big system, which is going to build up very, very fast, I would say. Let's dig a little bit more into details and move to the first one, which I would like to propose today, is acoustic method. Again, I hope you can see the animation here. It is very, slowly varying. And in this case, what I'm showing you is a gel. This is a typical IGBT module, a gel filled module, where because of power cycling, again, you have some movement inside the gel. And this is basically thermal, let me call it breathing. So because of temperature up and down, basically the gel expands and contracts. And what you can see here is clearly observable because of deflection of light here. So this is something we cope with. This is happening now, here and now, in our IGBT modules, right? So we have to be able to somehow monitoring what's going on there. So let's start with acoustic methods. Acoustic methods is definitely suitable for degradation monitoring, which is very highly demanded. In itself, I would say, is not new. For example, ABB has been proposing, and actually they have a commercial product for monitoring of, state of health of motors. State of health of motors. So they put basically a pad on the side of the motor, and this pad monitors vibration and compares with the database, again, of vibration patterns. And in case of large discrepancy, they can conclude something is going on, maybe at the bearing level or something like this. However, this kind of method has been successfully demonstrated also on power electronics, for example, in polypropylene capacitors. You can see a picture here where they put a sensor, an acoustic sensor, in this case, very expensive, very large bandwidth, and something like this on a capacitor, and they could detect what the state of health was for this capacitor. The principle is applicable also to bond wires, like in this case, this previous slide. So what we did at Tilburg University, you can see some pictures here. What we did, sorry, I forgot the reference. Sorry about this. I will put it before sending out my slides. What we did here is to detect a change in sound of basically magnetics and on top of them bond wires. So we managed to put a sensor inside. You can see it here. It's small picture. Sorry, maybe I can magnify a little bit. Let me try. Yes, it worked. So you can see the sensor here, but the plan is to use a very cheap microphone for mobile phones, very small, very cheap. You can embed inside the module, and you can see some encouraging results here. This is what is called the output, the magnitude of the output signal. You can see that according to the number of cycles, basically according to the wear out of your component, basically the acquired output power, sound output power increases. To achieve this result, however, you need to use a complex signal processing. So, you know, the pro is that it is fully contactless, which is very, very good. And you don't need a strong calibration. You just start recording your sound, and then you compare the sound after months or years, and you see what the difference is. The cons is that, of course, you don't have a lot of sensitivity, so you need to wait for severe wear before detecting it. And also you need quite a big and powerful signal processor, because you need to perform FFT on your signal. So the sensor is cheap itself, but you need to make a large post-process, like, you know, FFT, as I mentioned before, filtering and sampling and so on and so on. This was about acoustic methods, which are very promising. And nowadays, let's move to a little bit more established method, for example, optical methods. So I would say optical methods can be classified into infrared or visible light emission, optical fibers, and infrared detection apparatuses. Again, a video for you here. I hope you can see it moving, and you can see this is a video taken shot with an infrared camera, fast infrared camera, during a short circuit of such kind of prime pack modules. So you may probably recognize the squares here. The 6 square, 1, 2, 3, 4, 5, and 6, which correspond actually to the IGBT chips here, which are subjected to short circuit. And because of the because of the infrared camera, thanks to the infrared camera, we could detect the hot spot, the hot points inside the module. This is also a work we did at Aalborg University. I mean, I may agree it is not 100% condition monitoring, it's more laboratory testing, but I will be spending some words about this and how important also infrared detection techniques are. Right, let's start with the infrared visible emission. Basically, the idea is very simple. There are some semiconductors like silicon carbide, which are able to have what is called a direct recombination mechanism. If you are familiar with the band gap of semiconductors, you may know that basically electrons accumulate on the top side, which is called conduction band, and holes accumulate on the bottom side, which is called the valence band. During current conduction, what happens is that you have electrons, which is moving, which is called basically electron injection. And you have a probability that one electron finds a hole and they recombine. Recombine means basically they disappear, but their energy doesn't disappear, cannot disappear by conservation of energy. And this means that the energy difference, which is corresponding to the band gap, is emitted by means of light. Silicon is not like this, because silicon has no direct recombination. There is no way you can get this out of silicon. But other semiconductors like silicon carbide can do this, and actually this feature can be positively exploited to do this. In particular, silicon carbide is very well known. It emits light from back to 1906 or 7, so basically more than 100 years ago. And when they still called it carborundum, because it was mostly known for basically its mechanical properties, its stiffness and its hardness, rather than its semiconductor properties. Nevertheless, this phenomenon was very well known, and it is possible. It has been demonstrated also at Aalborg University, not only, but also at Aalborg University, it has been demonstrated that it is possible to correlate temperature with light. The reason is very simple. Sorry, temperature and or current with light. The reason is very simple. If you have a different current, you have a different emission. Of course, it's quantity of photons, very simply. But the interesting thing is that if you have a different temperature, then you have to know that the band gap, the band gap width is temperature dependent. So if your temperature, in particular, it shrinks, it squeezes with temperature. In particular, if your temperature increases, your energy decreases, your band gap energy decreases, and your wavelength becomes longer, right? So in principle, you can detect the color, right, of your radiation, and you can work out what the temperature is. This method sounds very, and you can see some pictures here, basically in current up here and in temperature down here. This method is in principle possible, but sounds very expensive because you need a spectrometer. So what you can do is actually to use a visible light detector, which has very, very narrow optical band. If you have a very narrow optical band, you're basically focusing on a limited range of frequencies or wavelengths. Then when your temperature changes, basically you are moving the emission peak and you are moving the amplitude inside this band. And you can work out what the temperature was. It is not extremely sensitive, but nevertheless, you can see here a nice picture of a calibration operation we did with such kind of methods. And you can see that for a given current, you have a very nice correlation between temperature and output voltage. Of course, you can see that we are talking about 80 millivolts, 100 degrees Celsius. So this means basically that you have some fraction of millivolts per degree Celsius, which is not incredibly sensitive, but still something meaningful. Very good galvanic isolation, very low cost sensor. I told you everything you need to know is to find a narrow band detector. The cons is that it is slow because basically the sensor is based on energy brought by photons, so you need to wait, and this can take also milliseconds or more. And you need calibration effort because basically ambient light, you need shielding, you need to make sure that your light, the light you're measuring is really the one you want to measure, nothing else. Optical fibers. In the beginning, optical fibers were not a condition monitoring method, so I was still in doubt to put them or not. Actually, nowadays, there is a very, very strong effort in embedding optical fibers into IGBT modules. Of course, we are talking about, I would say, high-level applications where the value added is relatively high and you can afford it. And definitely, it can be, I would say, primarily used for temperature monitoring. You can also use it for vibration, but principally it is used for temperature monitoring. And the obvious pro is that you get the galvanic isolation and very low EMI issues because it is optical, driven signal. So you can bring your signal actually even 10 meters apart from your electronics, which basically makes an intrinsic shielding against electromagnetic interference. What about the cones? The cones is obvious. Optical fibers are not bringing an electrical signal. You need to convert this, and you need to do this by interferometry techniques. So what people do, for example, this company, which is a world leader, sorry, in optical fiber production, optical fiber sensor production, what they propose as a solution is there's a signal conditioner board, which is worth some $100. So you cannot really afford because it is even more expensive than the IGBT module itself. So you have to be really using this for high value added applications. Anyway, I know for sure because I'm in contact with them that they're working hard on making this conditioning unit a lot cheaper. In this case, this is game changing because this means that you can really provide your module with optical fibers by factory, and then you connect with the monitoring unit and you have intrinsic, condition monitoring feature. I mentioned in the beginning, infrared detection apparatuses are in principle not a condition monitoring method, are rather a diagnostic method. The reason why I mentioned them is because basically they are almost the only way we use to calibrate other condition monitoring methods. So it is rather used as a reference, I would say. The reasons are manifold, I would say. First of all, it is very fast, so you can really detect what the change in temperature is before your sensor is aware of it. The second reason is that you get the temperature distribution, a typical screenshot here, rather than a single point. So you have a better picture of how your temperature distribution looks like. Of course, cons is that it's very expensive. It can be really, really expensive. It can be 1 million Danish crowns or even more when it comes to very professional cameras. And what is an intrinsic drawback of monitoring temperature with infrared cameras is that emissivity is very low because all the chips are covered by metal. So doesn't matter, you have the gel covering them, but the problem is that because of metal, emissivity is low, and basically you either need to work in a dark environment. You can see here a detail of this black tube we have been using here to shield all the environment and to make sure we are shooting at the only light in there is coming from the chip only, or you need to remove the gel, you need to black paint, but this means that you are losing the big advantage, which is your very fast detection. So let's move to physical or in contact methods. You may know, you may not, thermocouples have been also proposed as a cheap and convenient method for condition monitoring, in particular temperature monitoring. It is cheap, it is a reliable method, it is very simple. All in all, you have to inject a current and measure a voltage, which is something really doable. Cons are many, very slow, because you have a metal which has a big thermal inertia. So basically what you can measure is just the average temperature over seconds, basically. It is a metal conductor, and you have to measure millivolts. So it is largely noisy and prone to EMI, electromagnetic interference issues. Galvanic isolation is very critical. You can cover, this is a table where you can see some typical coating materials you can use for protecting, by galvanic contact with some nice, I would say, kilovolt rigidity. But another story is how reliable this is, and also, which kind of glue, because whatever the glue you use for contacting this thermocouple has to be subjected to the same temperature variation of your chip. But anyway, this is a possibility. This is a real possibility. And then we move to electrical methods, which are by far, I would say, most popular nowadays. So basically, there are several approaches. I will start from thermal test chips, which is basically a method for embedding a sensor inside the chip. And then I will be largely talk about the thermosensitive electrical parameters, and more specifically, on-state voltage drop, peak gate current. I have two here for on-state voltage drop, peak gate current, flat band voltage, measurements on auxiliary emitter resistance, and dynamic temperature sensitive electrical parameter. Let's start with the thermal test chips. This is nothing really new. It is at least 10 years. It has been given a proof of concept of this. Basically, the idea is that you have a chip, and you can fabricate inside the chip itself, you can fabricate a sensor, which is basically a diode chain, like in this case. And because the diode, what is called the knee voltage, which is typically 0.5, 0.6 volts, something like this, it is temperature dependent. And because you are in the very middle of your chip, then you can basically measure, you can infer what the chip temperature is by just measuring the voltage drop across the diode chain at a given reference current. It is possible. It has been demonstrated in this case by the authors. They also demonstrated an auxiliary emitter for current measurement. So they modified the chip to put an auxiliary emitter for current measurement, but in this case we are more interested in the temperature here. And basically what you can do is also to integrate the resistance, which is larger in area, and oh, by the way, I forgot the most important drawback here, which is actually the area. So you are wasting active area to embed this chip and its contacts. You can see here, you cannot really use the area underneath the pads. So you are wasting area because of the sensor there, which is a big drawback because area in semiconductor world is money, basically. But you can do this. The other drawback of using resistance detectors is that they are larger than diodes, so you tend to use diodes because they are smaller. Very linear, by the way. You can see a picture here that's impressively linear, very good sensitivity, not bad. This is voltage, by the way, not millivolts, it's volts, right? Not easy galvanic isolation. You need to provide bond wires here. You need to contact the sensor with bond wires. So you basically don't have galvanic isolation, which is a nightmare. You have measuring bond wires which are 100 micrometers apart from high voltage. I can agree with you. This is the emitter. It is low voltage, but you know, here you have a DBC and here you have high voltage. So it's a big problem. And you need additional bond wires, which means you don't just need the cost of bond wires, which is nothing, but you need the DBC, you need the layout of your module, which is enhanced, and you have more area wasted in your DBC because you want to bring your sensor signal out of it. And of course, it is prone to EMI, each sort of EMI. We're on the very chip, so you can imagine how fast and how intense current and voltage transients are here. TSEPs, temperature sensitive electrical parameters. There are so many. I could just find an excerpt of them, just a selection of them. On-state voltage. You may know, you may not, that most of semiconductors, like IGBTs, have a temperature dependent on-state voltage drop. Like in this case, this is VC on, and this is current. This picture is normally seen with the swapped axis, so you can see the voltage on the first axis and the current on the second axis. This is just the same picture. We just use it in the opposite direction because we want to point out what the voltage dependence is. You can identify basically three regions, which is called the PTC, positive thermal coefficient, which is called NTC, negative thermal coefficient, and the blind region, where unfortunately you have no significant dependence on temperature. What you can do with this? Well, if you can afford to wait for your current to get high, for example, in a sinusoidal case, then you trigger your sensor at this current level, and you have a very nice dependence of your on-state voltage on temperature. So everything you need to do is to synchronize your modulation with your sensing electronics. And what is also a very good idea to be measuring it far away from the transient, turn on transient and turn off transient to avoid the noise, basically. And then you wait for a second trigger, which is the high current trigger, and then you measure it. You can see here a typical measurement circuit, which is very nice, very simple, and also very, I would say, bright solution. You use two matched diodes which have the same temperature, and the circuit is such that the voltage drop across the diode cancel out. So whatever the temperature doesn't matter. And this diode blocks the voltage when your IGBT or whatever your device is off. So this means that this voltage is not dangerous. This high voltage is not dangerous for your electronics. But when it is on, you can correctly measure the on-state voltage. So no need for additional sensors. The additional circuit is very simple, relatively simple. And you can both actually monitor also the diode operation, because this voltage here can also be negative, no problem. So when the current is actually going the opposite direction, you are biasing the diode and not the IGBT. And the voltage here is the voltage across your diode, so no problem. You need an extensive pre-calibration process because everything depends on, depends on current, depends on, of course, on temperature. So you need on the specific IGBT and also on the layout, it is possible to show. So you can see some results here where both the, I think the red curve is the diode one, and sorry, is the IGBT actually. No, it's not like this. So the red curve is for the high side and the blue curve is for the low side. And you can see that maybe opposite, red low side, blue high side. And you can see that we monitor both the IGBT voltage and the diode voltage, which means we can monitor both IGBT temperature and diode temperature. Another drawback of this method is that, as I mentioned in the beginning, if you never reach the high current level for a long time, for example, if you think of a wind turbine, which is basically most of the time working at 15% or 20% of the full load, then basically you are working all the time in this region and you are missing days of condition monitoring, of course. Another on-state voltage drop method, which is totally different, but the principle is basically the same. You want to measure VC voltage, and you do this with a, I would say, nice and bright solution, which is adopting a depletion MOSFET. Depletion means normally on. So basically, you can imagine this MOSFET as just focus on this cell. You can imagine this MOSFET as normally on, so which means that the voltage here is the same as the voltage here as far as you have no current through it, which is very good. So basically you can drive your voltage, your collector voltage all the way to the amplifier. And of course you need some protection and that's it. And you can put MOSFETs in series if your blocking voltage is not enough. What happens during the off state? During the off state, this voltage is very high. So the drain tends to be, high voltage, but you can see the gate is connected to the source. So this means when the drain voltage increases, basically the current here increases and the emitter voltage, the source, I should say, voltage increases. And this means that the gate to source voltage becomes negative. And it becomes more and more negative until this MOSFET turns off. And this protects the electronic against the voltage, the high voltage. This circuit works also for negative voltages, so you can also monitor the diode here. And it also works for for the low side, if you just pay attention to referring your voltages to the middle point here. So voltages with reference to the middle point are VTC plus for the high side device and the VTC minus for the low side device. So at the same time, with the same circuit, basically, you can measure all four components. What is the obvious drawback is that your reference voltage, which is called out, in this case, phase out, is switching up and down at switching frequency, right? So everything here should be very, very carefully shielded against conducting the EMI, electromagnetic interference. And by the way, it is patented, so to use it, you have to pay some royalties. Peak gate current, this is very interesting, very promising. The idea is you want to monitor your temperature on the gate side, and the idea is very simple. Think of turn on sequence. At turn on, your gate is initially low voltage. It can be 0 volts, it can be -5, -10, doesn't matter. Because you are in the gate driver. And when you turn on, basically because of the capacitance, the input capacitance of your IGBT or whatever the MOSFET, this voltage is fixed. So this voltage is, for example, 0 volt, and you are pumping 15 volts, and you exactly know what the voltage difference is. If you know the voltage difference here, well, you know the current because you can measure the current by a differential amplifier across this resistor. This is the gate resistance you put anyway. And then you know the voltage, you know the current, you can work out the value of this resistance. But this resistance is the embedded gate resistance in your chip, whatever it is, MOSFET or IGBT. And this one depends on temperature. So this internal resistance depends on temperature. So basically what you can do is to infer what the temperature was because of the change in resistance value. You can see here a nice screenshot of what happens during transient. The black one is the gate voltage, and the green one is the voltage across the measurement resistor, and the red one is the output of this circuit, which is also including a peak detector, basically a sample and hold circuit, so that this voltage here, the red one, the final voltage, is proportional to the current which has been getting through the circuit. So you can work out easily what the current was, what the resistance was, and what the temperature was. The temperature sensitivity is unfortunately not that high, and also you need quite a large calibration. This is as a con of this method. Oh, the obvious pro is that you are using a gate circuit, so you're not measuring the collector voltage in no case, so it is intrinsically safe, right? And by the way, there is another pro, which is also very important. It is not current dependent, so it is not load dependent, which is very important. So you don't need to calibrate in current. Another method, which is rather theoretical, I would say, is what is called the flat band voltage. You may know, you may not. The input capacitance of MOSFET or IGBTs depend on voltage, on the gate voltage. It drops because it goes into what is called an inversion. It is called depletion region and then inversion region. But this drop happens at a voltage which is temperature dependent. This voltage is called flat band voltage, and you have an evidence of this voltage by the change in slope during the turn-on transient. I'm sure you are very used at these waveforms, but you probably have never noticed this change in slope. This change in slope has a reason, and this reason is called flat band voltage. This flat band voltage changes in temperature. So in principle, if you're able to detect this change in slope, then you are able to detect this change in capacitance. Hence, you can infer what the temperature was. This is very theoretical, however, because you have a big limitation in the fact that if you change this, if this voltage is not stabilized, is not regulated, everything changes. There is an additional bias. So fluctuation are very critical. And also you have to work out a second derivative detector. So change in slope means working out the second derivative, which is quite of a big challenge when it comes to a noisy environment. Auxiliary emitter resistance, this is also very promising. You can see a prototype here in this picture here. The idea is very simple. You put, if you have a Kelvin contact, which means an auxiliary emitter, then you can put a resistor on this branch like this one here. If you put this resistor and you put a simple current generator, which is basically monolithic integrated circuit, very low cost, and an instrumentational amplifier, then you can do a magic thing. So look at this. During off state, basically the bond wire voltage drop is 0 because there is no current here. So you can regard this part as a short circuit, and the current generator is a circulating current through this auxiliary resistor. But if you mount this auxiliary resistor on top of the chip, you can see a prototype here, then you are able to work out what the temperature is, because this is temperature dependent. So you can see a typical pulse given during the off state of your IGBT. But that's not enough. You have more. During the on state, you can turn off this current generator. There is no current here. Sorry, during on state, I meant. You can turn off everything. You are in the on state, in the on conduction. So what you can do is to use this same operational amplifier to monitor the bond wire voltage drop. So you have both temperature and degradation monitoring. Yeah, there is an obvious con, which is the auxiliary resistor must be put on chip top or even integrated with loss of area, of course. And if you put on top of it, a big question mark is about reliability of the glue you use to do this, or whatever the alloy. Dynamic temperature sensitive electrical parameters, which are very, very promising, they are founded on a very simple principle. Again, you need to use a Kelvin emitter or source in the case of MOSFET, and you have to monitor with your monitoring unit the voltage difference between the Kelvin emitter and the power emitter. So this voltage difference is actually made up of two components. The first one is this stray inductance component, and the second one is this stray bond wires inductance component. So you can see the total voltage can be written as the summation of this voltage drop here, inductive voltage drop here, and this inductive voltage drop here. But the interesting thing is that during normal operation, you can see here a sequence of turn off first and turn on. So you can see the current here, turn off, turn on, and the voltage, turn off, turn on. Well, the interesting thing is that you have current. This is, by the way, gate voltage in green, and this is gate current. The interesting thing is that you have a current through this inductor at times which are different from when you have a current through this inductor. So they are separated in time. So look at this picture, which is plotting, which is showing you what the voltage drop is across this Kelvin to power emitter. So this pink, this waveform on the bottom here is the one related to the voltage drop here. And you can easily recognize that this peak here is related to the strain inductance on the auxiliary emitter. This one is related to the strain inductance on the bond wires, again auxiliary emitter, again bond wires. What is very interesting is that if you have anything here, for example, T off time, which is the time between the gate peak and the real turn off instant. If you have this turn off time, which is dependent on temperature, which actually is, then you can easily measure the delay between this peak and this peak, and you can infer what the temperature was. That's not enough. You can do more. You can do a lot more. For example, if you look at this slope, the current slope, it is well known. It is also temperature dependent. So if you change this slope, actually you're changing this derivative here, and you're changing the amplitude of this peak. So if you're able to measure this peak, this is not a time measurement, it is an amplitude measurement. You can do with a measurement amplifier. Well, if you measure this peak, then you are able to infer what the temperature was. Also, the area here corresponds to the amplitude of your current, basically, because it's the derivative. So you can work out what the current was. And again, is not enough. You can do a lot more. For example, during turn on, you know there is this peak, and this peak is related to reverse recovery of freewheeling diode. So this reverse recovery is speaking, is a well-known phenomenon, but it is temperature dependent. So this means that if you change your temperature, this peak will change, and also it will also change the second part slope. So if you see what this means, you can see that this peak is changing in time. So if you're able to monitor this time, the zero time here, so you need a zero detector, which is even a different concept, then you can infer when the peak was, and this is also temperature dependent, or you can measure the slope. And if you measure the slope, you just have to measure this negative peak, and you can also infer the diode temperature. So just by monitoring this Kelvin to power emitter voltage, you can not just infer the IGBT itself temperature, but you can also infer the freewheeling diode temperature, which is sitting on the other side of the bridge leg. And there is a lot more here you can do, actually, playing with these numbers. There are also some cons, of course. You need relatively accurate time detectors, otherwise, for the timing part, otherwise your sensitivity is low. Or you need the digital hardware for integrating when you need integrals, as I mentioned before, which is quite an expensive thing. All right, almost on time. We can move to conclusions. So here you can find a recap of the most popular, I would say, methods for condition monitoring, and definitely there is not a single one. I wouldn't say there is a standard condition monitoring method. Actually, there are many, and all of them with pros and cons. I'm not quite sure which one will prevail in the coming future, but definitely I would say is a key message. I would prefer the one with galvanic isolation, so contactless methods, or if this is, if it is not even possible to modify the module, the package, whatever it is, with optical fibers, with acoustic sensors and whatever, for some reasons, then TSEPs are definitely, I would say, prevailing. as a conclusion, I would give you some take-home messages. So first of all, power electronics has become, over the last 4 decades, an enabling technology. No doubt, you remember I've been talking about this and pointing out how energy is nowadays conditioned from the very beginning, from the production to the consumption. So conditioning, power electronics means conditioning energy and ensuring, continuity of service. So this is very important. The last 2 decades have shown a condition monitoring blooming, basically, with many concepts and technologies. I've been showing you some. The last one was about dynamic TSCP, temperature sensitive electrical parameters, but there are so many you can find over the literature. It is good to bear in mind that communication infrastructure is essential. So when you may remember this picture, when I pointed out that, yes, you do condition monitoring, that's very good. You monitor the state of health of your power electronics. This is very good, but then what you do with this information, you need to process it sooner or later. So you need to, to embed this into a bigger and even bigger infrastructure, which is basically spreading at system level. What's next? Maybe a question is, well, I pointed out in this slide here that probably the new coming technologies in condition monitoring are artificial intelligence, interconnections, which means basically communication infrastructure, Internet of Things, and cloud computing, last but not least, because you have to remember that to make decisions based on artificial intelligence, you need quite of a, I would say, powerful computational infrastructure. I provided in this presentation also all the references about this work, so you find them here in the last slides. And as a general reference, you may refer to this open access paper, which has been recently published last year, basically 2 decades of condition monitoring methods for power devices, published by MDPI. I think this concludes my webinar. Thank you very, very, very much for your attention.
Thank you very much, Francesco, for this comprehensive overview of monitoring methods, a well-structured presentation. Thank you very much. So now we are looking forward to questions from the audience. Please raise your hand, the ones who have questions, and then we go on. Yes, Per has a question, please.
Yeah, little bit generic one. It's very, very interesting presentation, this. Thank you. You pointed out the sort of a balance on where you do the analysis. You do the measurement, of course, on the system itself, but then you go to the might be cloud also for taking the decisions. But there is a balance. What do you think? Will we do as little as possible in the power electronic systems and go outside for what as soon we can, or do we try to do as much as possible locally and limit and make it more general centrally?
Yeah, that's a good question. I mean, I'm not an expert about intelligent decision making. Actually, it's matter of money, basically. So if you want to make artificial intelligence based decision inside your electronics, probably your electronics is going to cost a lot of money, because the computational unit is not trivial. You need a microprocessor, you need the RAM, you need a lot of things. You need an internal database where, I know little bit of artificial intelligence, but what I could understand from the very beginning is that you need resources. You need the computational resources, you need storage resources, and something like this. My feeling is that we are moving toward the centralized centers. So maybe you can keep your unit as cheap as possible, just providing a communication infrastructure. And that's the minimum you have to do. You have to do it anyway. And then all the decision can be made, I would say, far away. But of course, this is dangerous. This opens another scenario, which is safety. I mentioned it very little when I talked about security agents here, but it's a big issue, because then this means that you can have big accidents because of centralized information. So I'm not sure what the decision is. I'm quite sure actually it's going to be cost driven.
Yeah.
Yeah.
My experience in industrial applications here is that many customers are very sensitive about the security of that information. So that is many times been a big no.
Right. You're right. But I mean, without knowing it, we're getting used to this. For example, we are recording this meeting, right? Do you know where this recording is going to be stored? Not in my computer, not in yours. It is probably somewhere in California or in Alaska, maybe, where they have this big computer farms, right?
Yes.
Yes. And we don't know. And it is working, and it is so nice. It is working that we don't even, we don't care, basically. And my view is that it's going to be so easy when you can offer the customer a turnkey solution, right? So the customer would not even know how the data is processed and what the data flow is, and something like this. So yes, it is a matter of culture, but if you want very reliable power electronics, you remember I mentioned even 30 years operation and something like this. It's in my opinion, is the only direction to go.
Okay.
Yep.
Okay, Tag.
Yeah. Assume that we measure the temperature and we know that. How will we affect the electronics? I mean, should we reduce the power output, or what? Or should we increase the cooling, or is it to predict the life length? Or how are we going to use the information we are collecting?
Actually, your question is also a nice answer. I mean, the three things you mentioned are one better than the other. Of course, you can do what is called a smart derating, and this is possible in many applications. There are applications where, unfortunately, you cannot. For example, if you want to regulate the speed of an axle, then you cannot do any smart derating, because the speed is given. But if you are pumping up some water, in principle, you can reduce the pressure if it is allowed by the policies and by the operating protocols. And this is regarding, of course, when it comes to wind and solar power, you can waste energy, but you can make smart derating. So you can reduce the produced energy because of reliability issues. So you can make decisions like this. And this is definitely one good point. You can play with the cooling system, definitely, no doubt. And I would say in the other direction. So you can save cooling power, for example, the fan speed, which is also taking some power, reducing the overall efficiency. Just, if you are aware about the junction temperature, if junction temperature is not high, is not too much high, then you can reduce the fan speed or even turn it off in principle. So you can do something like this, definitely. And yeah, I mean, you can make lifetime prediction, and this is also very amazing, very interesting. And this enters a little bit another world, which is called digital twin, where people use basically field data taken with condition monitoring to train a neural network, again, artificial intelligence based digital twin. And digital twin, it is basically a model running on your computer or on a supercomputer, which is gonna behave like your real converter. So it's learning in this case. I agree, and I can tell you more about what else you can do. But you can also do load balancing, for example. You can deliver the same power, but if you have a coordinated system, you can tell the other converters to pump more power into the grid, and you can reduce the power of this one, and similar things. If in principle, what to do with the state of health, or with the temperature, or with both of them, it's another story. It's a science, if you want. It's also, you know, also I would say strategy. I would say science or something like this. I hope this answers your question.
Yeah, thank you very much.
Thank you.
Any more questions, please?
I have a question, by the way. I mean, if you don't mind, Mietek, is there any group or subgroup in your Wabanga Power Center working actively on condition monitoring?
Per?
I wouldn't say so. There are no groups working on different things in that sense. There are projects run by the individual members or in consortium, and through the time we have had some projects on, for example, reliability. We looked a little bit into reliability on silicon carbide, but that's quite some time ago. So okay. I would say that there's nothing actively ongoing.
No. Okay. So it's also a good opportunity for collaborating. Probably.
Yes, it is.
Because you are very strong on converters, I know for certain. Very active, also very good industry connections. So it could be interesting to investigate.
Yeah. Once I have the hand up, the presentation here was mainly or almost dominated by power semiconductors, not on the passives. Did you do anything on the passives like capacitors and inductive elements?
Yes, you're right. That's a very good point. Not I myself. I'm a semiconductor guy. I didn't introduce properly myself. Sorry about this. My background is about semiconductor physics. So it is biased somehow. You're right. But my colleagues at Aalborg University, in particular at Corp, they also work on condition monitoring of capacitors and a little bit, actually, just the isolation level on inductors. So nothing on magnetics, but you know, coatings of enameled copper and something like this. I know for certain they are very active on capacitors, and they can detect, for example, drift in time of ESR, equivalent series resistance, and also loss of capacitance over time, because basically the intrinsic structure of your capacitor, you have a lot of plates which are in parallel or just wound together, and then the side contacts get degraded over time, and then the overall capacitance decreases. So the answer is yes, there is a lot which is done there, and yes, it is a lack of information here. Sorry about this.
Oh, no problem. But it seems like when you look on failure rates in power electronic system, it's dominated by the semiconductors.
Yeah, that's correct. Right.
Okay, Konstantin Kostov, before I let you in, I would like to answer shortly also Francesco. We have some within the European projects we work on, you know, like predictive maintenance, artificial intelligence, and physical based models for lifetime prediction. But this is all kind of research level.
Yeah, but if I may, I can turn your question in what is the state of the art? Where are we, right? Well, what I can tell you is that in the last 1 year, I got contact of, I think 4, if not 5 companies, all of them asking us for contracts, large money, by the way, big money, for condition monitoring. So the answer is that I feel like the answer is that we are not there yet. Oh, condition monitoring and also lifetime prediction, by the way, which is also something they're very much interested in. The uncertainty in lifetime prediction is not acceptable anymore. They want to know with the 1 year approximation, it is going to be 14 or 15 years. You have to tell me something like this. So the answer is that we are not there yet. This is really something we have to work on, and there is a lot to learn, a lot to do there. And I personally see the only solution to do this is through condition monitoring. Whatever the lifetime model you work out at time 0 is not aware of all the mission profile, all the real life your power electronics is going to be through. So the only way is to continuously monitor, which is of course more expensive than making one model at time 0. But the only way, in my opinion, is to continuously monitor, and then, as we discussed before, to make decisions on the go. So trying to make things as smart as possible. This is my view.
Okay, thank you. So now Konstantin Kostov, please.
Sorry if my question is too stupid. I don't work in the area. So when we have a module, we are paralleling chips.
Yes.
And let's say we use this, let's say, monitoring of on-state voltage or the gate current. Do we monitor individual chips or all these chips in parallel? Because in a module, we usually have them in parallel. We turn them on and off simultaneously. At least that's the goal. But what breaks is individual chip.
Yes. Yes.
So what do we do? And I mean, I think it will be very complicated to monitor individual chips.
Your question is actually not stupid, and what I'm used to say, let's say to my students, is that there are no stupid questions, but only stupid answers. Your question is very appropriate, actually. Actually, it's a very hot point, because when it comes to modules, I've showed you before, this module has 6 sections in parallel, right? The one with the movie. So yeah, this one is 6 sections, each of them 4 chips. So when you have 6 IGBTs working in parallel with 6 diodes in anti-parallel, how to work out the single temperature? It may be, you could see also from the video, the temperature is very different. So it can be 10 degrees plus minus. And actually, I can tell you even more, because it can be 20 degrees plus minus inside the same chip, because the temperature distribution inside the same chip can be uneven. So it's basically no go. I have no answer to this. But what I can tell you is something quite interesting. If you stick on this method here, this one based on the auxiliary resistor, well, what I can tell you is that basically it is possible to place one single resistor for one single chip. So each chip with its own resistor. And this is also under patenting process. I'm working on this. But basically what is possible is to use a slightly different value of your resistor, auxiliary resistors, because I didn't tell you that this value is critical. It is not. So in principle, you can play with different values here, and you can make a smart circuit here, which is able to recognize what is what. So which resistor is changing, right? But this is also theoretical at the moment. So the answer is yes, it is not possible. No, it is not possible. You have many chips in parallel. You have only one gate terminal. And inside the same chip, you have uneven, strongly uneven temperature distribution.
Okay. Any more questions, please? Time is running. So I don't know, your presentation was very clear. Very
yeah, thank you.
Comprehensive, as I said.
Thank you,
but a lot to digest.
Yeah, it's fine, no problem. But let me invite you all to contact me. I think I put my email address somewhere, maybe in the beginning, yes, or probably also in the end, yes. So you can find my email address here. So as soon as you receive these slides, you're welcome to contact me if you are interested, whatever it is. It could be some clarification about the presentation, but also some, interaction possibility, some collaboration, some common project application, starting from you, of course, Mietek, but also I know some of, I could recognize some names here. So definitely it would be nice to do something together. Of course, I'm also thinking of Horizon Europe, which is now very close to be starting. The calls are already there, so it's just waiting for the opening deadline. And and to be honest, there is already a project I'm involved in together with KTH. So I mean, source for endless collaboration.
Yeah. Thank you very much for this invitation. This is also sometimes I think from the companies, on the company's part, it's maybe easier to ask a question directly to you than ask it like this on the forum. So yes, very good.
Yes.
So shall we say that we are happy with this meeting? So let's thank Francesco Iannuzzi one more time.
Thank you.
Thank you very much
for having me here. Mietek, I will send to you my slide PDF, and as agreed, you will be distributed among the participants.
Yes, thank you very much.
Thank you.
Good. See you next time at our SCAPE conference or at another conference.
Absolutely. Yes, we missed it because of COVID. Definitely.
Yes. Right.
See you physically then. Bye.
Okay, see you. Bye.
Bye-bye.